All right. So our goal for this video is to talk about constant acceleration kinematics in one dimension. And these are some keywords to remind me what to say. Give me just a second. All right. And so in the last video, we talked about the general definitions. And now let's get down to work with some practical applications in one dimension. When we do that, it's not going to look exactly the same as the definitions in the last video. I'm just trying to match up to what most people use most of the time on a practical day-to-day basis. And usually when we're doing 1D, there's a little bit of a focus issue there. Let me see if I can get that dialed in here. All right, that looks pretty good. Sorry about that. What we really do is these equations are usually written on an equation sheet of some kind that you're handed out. They might look a little different. I'll explain that. But we're going to try and use these equations to solve real life problems. If you're curious where these come from, I'm going to show you something really quick. If you don't understand calculus, what I'm about to show you is not required, but some people might like this to see it. Give me just a second. Come on. So if you're curious where this comes from, it comes from the definition of acceleration is the derivative. Again, you do not need to know calculus if you're in physics 110 with me, but if you're in a calculus-based physics like physics 161, you would need to understand this. But if A is, you could separate this. So we have the dv on this side of the ADT. You could do an integral. You could use some limits to avoid a plus C issue. When you do that, you get this. It's great. Now you can do this, blah, blah, blah. We basically get an equation for velocity as a function of time. This V final would be, look, you tell me the time, I'll tell you the velocity at that time. This is an equation for V as a function of time. You could repeat this process using V equals dx dt and figure out these other equations. Point B, these equations right here come from this process. If you're in physics 110, you don't need to know this. So let's focus on the task at hand. Right? Our goal is basically to figure out how we use these equations. To be clear, many instructors will oftentimes write these a different way. For example, delta x, that means x final minus x initial. But I'm going to rearrange this equation in a little bit. Some teachers will write this as x final equals x initial plus v initial x times time plus 1/2 a sub x t squared. These two equations are identical, right? It's just a matter of whether you use x final or x initial. What do these symbols mean? Let's go through it. X initial means initial position. It is not initial distance, it's position. It's where it's located. X final, take a guess. Final position. And here's where it starts to get kind of annoying. V subscript I subscript X. V initial X. So the I stands for initial. X stands for horizontal. Or X. Now this V, there's no arrow on it, but you're supposed to know that's velocity. What? Isn't that frustrating? And I've been hammering on you over and over again to get these arrows right. Every physics book does it this way. Here's the issue. There's this mystery implied I hat on all of these things. So I'm going to put it in here for just a second. Time is not a vector. It doesn't need it. But what this equation really is saying is, look, delta x in the I hat equals the initial velocity in the I hat, et cetera, et cetera, et cetera, a sub x. Well, let me put all of these here. Final horizontal velocity. And then a sub x would be the horizontal acceleration. That's kind of sloppy, I apologize. Okay, Now you might be saying, dude, we're moving in one dimension. We don't have the y-axis. Yeah, but I also know chapter 4 is coming in a week, so we might as well actually get this right. The idea is you could write these same equations with subscript y on them. And if you did that, you'd immediately be able to do 2D or 3D kinematics. So just trust me. I want you to get in the habit of including these subscripts here, even though I agree they are unnecessary in my derivation. They weren't there. So just trust me. And I guess to be clear, I should mention delta x is x final minus x initial. All right. So now you could see that we've got these equations here. I'm going to erase this just so there's some clarity. The idea is we can use these vector equations, but not write the I-hats. And essentially, this number can be plus or minus. A positive number means to the right. I-hat means to the right. A negative number would be to the left, right? So you could have a velocity and you indicate the direction with the plus minus sign. Because there's an implied I-hat, any positive number would be moving to the right, any negative number would be moving to the left. Similarly, accelerating to the right, AX should be a positive number. Accelerating to the left, we should get a negative number. Okay, all right. And if you're curious how we get these equations, you could imagine plugging in, solving this equation for t, plugging it in up here, and then rearranging them, and perhaps you get these equations, or something like that. But and there are other equations too. I think there's 5 of these. Notice that this one has no v final. This one has no delta x. This one has no time in it. And there's various equations. You could have one that has no v initial in it, et cetera, or no acceleration in it. And these, they're great, but I'm going to tell you, I've been using these, I call the big 3 for forever. And they've worked for me for forever. Okay, so I like to memorize as little as possible. So I would just go with these. You use these 3 over and over again. You can get the other ones really fast with algebra. All right. So is there anything else I want to say before we do an example? All right. Yeah, I guess I'll say this. If you're in a different school or a different textbook, you might see sometimes people will use this symbol. Other teachers might use these symbols. I'll give it like a different color just so. Let's see if the paint working. Some textbooks or some people will call this x0. Some people will call this x. So what is going on here? I use x initial just to say the initial, but somebody else might say x at time equals 0, and that's why they use this notation. They're both great. I don't know why I just kind of got in this habit and now it's stuck. So similarly, somebody else might call this V0x and this just Vx. So there's the 2 styles you usually see. In both cases, we'll call this AX because it's a constant. Remember, this is a special thing here. We're talking about constant acceleration. This is a constant. To be clear, these equations are only true if this is a constant. All right, that said, a great many problems have this. Let's first start exploring there. Let's go do an example. So this is problem 2.1 1/4 from the workbook. What page is this on? So on page 23 in my copy. All right. So get that out. All right, so here it is. A plane is slowing to a stop with this rate, 0.175 Gs. Turns out if you accelerate much more than that, people can start to feel it really bad and get sick. All right, so to be clear, G is 9.8 meters per second squared. That is not gravity. That is not the acceleration due to gravity. This is the magnitude of acceleration due to gravity near Earth's surface. Okay, so it's not the acceleration, it's the size of it. So what we're saying is this is what, about, I don't know, about 20% of the magnitude of free fall acceleration, right? So, all right, that said, we're going to ignore parts A, B, and C of this question. You can pause the video and do those if you like. It's basically asking you about this statement. And anyways, let's go on to part D of this question. How far does this plane travel while it's coming to a full stop? And E, how long does it take to come to a full stop? First thing you need to do, how far, what are we looking for? What are we trying to find? How far is, in this case, delta x. That's what I'm looking for in this problem. I need to learn something about the change in the position. All right. Now, how long? That's a time question. So notice it's critical that when you're reading these problems, we start looking at the key words in the problem. How far away? That must talk about some kind of distance or displacement or position. I'm not sure which. I'll worry about it later. Some kind of delta x. How long? That's some kind of time. All right. So now, well, I can already see some trouble I'm going to have. I've got miles per hour here, meters per second squared there. The first thing I'm going to do is get everything in the same units before I, get ahead of myself and accidentally plug something in. So going back to chapter 1, I know that 1 hour is 3,600 seconds. And I know that 1 mile, the way I remember it, is you run tracks, 4 laps around a 400-meter track. So this is about 1609 meters is 1 mile. So let's punch this in. I got 170 times 1609 divide by 3,600, and it's about 75.98. Now in this case, this only has 2 sig figs, so I'll just keep 3. You know what? Let's get in good habit. Let's just keep 4 for all of our intermediate answers. So that is 75.98. Notice a quick rule is it's approximately divided by 2. It's not exactly, but that's pretty darn close. So, or going from meters per second to miles per hour is about multiplies by 2. I think the factor is actually 2.2. But yeah, anyway, you can figure that out and just punch it in. All right. So now that I've got everything in the same units, to me, it makes sense to kind of draw a picture here. I've started it. Here's where the plane comes to rest. Okay. So it helps to have a picture. It also helps if your picture isn't really freaking tiny so that you can label it. At the first few problems you do, a tiny problem, a tiny little, less than the size. As the problems get harder, your pictures need to be bigger. So get in the habit of drawing decent sized pictures. And if you can't label everything neatly, your picture's too small. Enough said. All right. Now I'm going to list my knowns and unknowns. And I'm going to give you a summary of this at the end. The procedure that I followed, I'll summarize it in a minute. But for now, I'm going to list my knowns. Okay, delta x, v initial x, v final x, a sub x, t. Okay, delta x, that's how far it goes. That I don't know. I'm going to just leave it as a question mark. V initial x. Now keep in mind, all of these have that implied I hat on them, except for the time. I'm going to draw that just this one time. Time does not have a direction there. So I don't know how far it goes, but I do know it's to the right. So I'm kind of expecting a positive number here because it went to the right. Right? V initial x. That's going to be my 75.98 meters per second. And I'm probably only good to the second sig fig because this one, as written, only has 2 sig figs. So this is just a rough estimate. We're keeping 4 sig figs because that's our standard practice. 4 on intermediate, 3 on rounded. Okay. V final x. Do we know that? Yes. At rest. That's going to be 0 meters per second. I don't even need the units if it's 0, but I threw them in there anyways. A sub x. Do I know that? This is where it helps to understand some units. I know anything that has units of meters per second squared has to do with acceleration. If you don't know how I know that, remember, we know that A is approximately equal to dv dt, or delta V equal to dv dt. It's approximately equal to delta V over delta T, but that's meters per second, which is meters per second squared. So if you're wondering, I'm kind of like, oh, wait, this has units of acceleration, or I could look at this word acceleration right there, that would help. So then think to yourself, what is AX? I'm going to punch in this number. 0.175 times 9.8 is 1.715. Okay. There's a problem with this. Think about it this way. I'm moving to the right, but I'm slowing down. That means I've got to be hitting the brakes. That means I need to have, in this case, an acceleration opposite the direction of the velocity. If I'm moving this way and slowing down, my acceleration has to be this way. If I'm moving this way and speeding up, acceleration will be positive. If I'm moving this way but slowing down, acceleration is opposite direction. I get a minus sign. Did you get that? Hope you did. Time, I don't know it. Okay, there we go. Let's go to the next question here, or the next part of this strategy. And again, I'll tell you a summary of the strategy in a minute. Wish I'd written that up before I started the camera, but I didn't. Okay. In this case, the next thing that I might do is use my kinematics equations from the other whiteboard. I'll just pop it over there real quick. Remember these equations? I'm going to write them down over here. Why? Because if everything's in the same spot, you're less likely to make a mistake. It'd still be on the video. Looks like we're just barely in there. All right. Next. The next thing that I like to do is plug in anything that's equal to 0. This might not be what you thought. Usually at this step, you might be thinking, oh, I should do some algebra. But first, if something is equal to 0, please stick it in because it will simplify the algebra. All right, hopefully. So I see that anywhere I see a v final x, I could set that to 0. Okay, there's nothing up there. All right, next, I can look at what is known and unknown and what I'm trying to find. Okay, in particular here, in this first one, delta x is what to find. So I'm going to look for an equation, if possible, that has some knowns and delta x in it. So in this case, I'm going to start up here. This is what I'm looking for. The initial x is known. That's something I know. T is unknown, not looking good. A sub x is known, but time is unknown. I think I use purple for that. Crap, not a good one to start with. Let's try the next one. In this case, the initial x is known. A sub x is known. And the time is unknown. Hey, already I see a technique that would work. This could get me the time. I could grab that time and shove it into here, or I could use this equation algebraically and shove it into there. But I bet that's what this last equation is. Let's run through this one. So that's looking promising. V initial x is known. A sub x is known. And delta x is what to find. So in this case, maybe eventually you'll get good enough to do this process in your head. But when you're first starting, do me a favor. list the equations, write the little checks and question marks for what's known and unknown. It just takes a little stress off you, and you let the paper do the work. You generally make fewer mistakes. Get it on paper, do the work, and hopefully eventually you'll make fewer and fewer mistakes. Once you get really good at this, then maybe you can take some shortcuts. But this is where people screw up, right? If they take too many shortcuts too soon, they make this more painful than it needs to be. So just let the paper do the work for you. All right. Okay. In this case, I'm going to go ahead, check this out. Rather than just shoving the numbers here, which you could do, why not do a little bit of work and do some algebra now and solve this algebraically first? Why? One, it's good practice. Two, that's useful if you want to code things or do things with computers later on. Three, it's just shorter, right? You don't have to write as many symbols when you're solving it, so you don't have to write this all out. And lastly, if you do make a mistake, it's oftentimes a lot easier to catch it in algebra than once you plug in the numbers, it's almost impossible. So whatever, there's lots of reasons. Let's do this. So I'm going to pull this over here. I'm going to rewrite this. 0 equals the initial x. Wait, let's just rewrite it. So now I'm going to move this term to the other side. Moving that over here. And now I'm going to make this positive and make that negative for a reason I really want to, whatever, I'm going to talk about it. Look, this the initial x squared is not going to cancel that minus sign. To be clear, maybe if I draw this in another way before I do this, let's remember where this came from. We had a negative this, and we have that. Now, if I multiply both sides by -1, you can kind of see that this minus sign is outside the parentheses. All right, we're going to square this thing, then multiply it by -1. No one writes it like that, so you need to understand that this does not get canceled by the square. This is how it's going to be written in solutions over and over and over again. So you need to understand when you see this, do not cancel that minus sign with that square. All right. After you screw it up a few times, you'll stop screwing it. All right, so then out of all this, what do we get? I think we get delta x equals negative the initial x squared over 2a sub x. Make sure that's still all on there. Come on, computer. Come on, computer. Whew, just barely. All right, so in this case, now I could plug in these numbers. All right, and when you do that, maybe I'll write up the final answer for you to check. I've got the answer written down here. Give me just a second. Well, actually, at this point, it's probably as easy to punch it in. I'm going to punch it in and get delta x. So I'm going to get the initial 75.98 x squared, divide by 2, divide by this thing, negative 1.715. And then don't forget, there's another negative. Notice this minus sign and this minus sign cancel out. If you got this right by missing both minus signs, that's not a good thing. That means you missed two things and got lucky on the easiest problem in the book. Okay, so really what you need to do is pay attention to your minus signs here and your minus signs there. Uh-oh, I'm in trouble. Okay. All right. Making videos late at night in the lab. All right. Let's finish this out. Here we go. Oh, what was the point? Shoot, I forgot the number. Oh, I plugged in all these numbers and I found that delta x is equal to 1683 meters. So about a mile-long runway. We could think about that a little bit. That doesn't seem outrageous for a plane landing needing 1 mile to come to rest. That seems totally plausible. I made these numbers up. I think I might have done a little bit of web research, but I don't remember. So this is not an outrageous set of numbers anyway. So this seems plausible. And likewise, we could do this equation, solve it for t algebraically. That should be negative the initial x over a sub x. Notice this minus sign will cancel this minus sign. and we should get a positive value for time. If you're not paying attention to your minus signs, you might have missed that. Okay, it's crucial that we do things the correct way here. So 75.98 divide by, whoops, I need negative 75.98 divide by negative 1.715. And I get what, 44.3 seconds? Now, I gotta get out of here, but, right, we could talk about sig things some other time. For now, let's just focus on these numbers. I hope this made sense, how I got these and how you might apply all of these theoretical things to a real life situation. We'll probably do another worked example in another video here, but I gotta stop this one.